call my number so it would go over the speakers, but I'm doing better today, so alrighty. So this is number 4A, so check these as you go, okay? What are the rules for adding and subtracting when you do sig figs? What is significant? The decimals, okay? So before I start a problem, I go through and look at this. Focus, okay? How many decimals in all these numbers here? This one we have what? Just one decimal. This one we have one decimal. This one we have zero. So the 0 decimals is going to be the one that controls my final answer, how I record it, okay? But I go ahead and I calculate like normal, plus, all these things together, and you get 435.2 milliliters, making sure you're including your unit. Knowing that this is an answer, but it's not your final answer. Your final answer needs to be recorded to correct sig figs or correct decimals with unit, right? So I see that I have 0 decimals. Looking at this number, I know that I have to truncate it here, but I need to see, does this 2 influence that 5? Does it round it up? No, so I just ignore it. Answer, final answer, 435 milliliters. And I'd like to see that. I'd like to see you calculated, and you're like, aha, I have to record to correct sig figs, and then you show me your final. Because it shows me your thought process and that you're actually thinking about it, okay? So, good with this one? Yes, okay. Now you're doing another addition. I figured we could do 2 of each. And when you add, how many decimals here? 3 decimals, and then we have 2 decimals. So who's the weakest link here? 2 decimals, right. So I like to say the weakest link because the weakest link of anything controls your final. So if you're a cross country, you got your relay races, I would be the weakest link, passing the baton to the next person, because you want to make sure you're thinking about what's controlling the final answer. So I like that analogy. So in the end, I want 2 decimals. So adding these together, you get 7.692 kilograms. I know that I can have 2 decimals, so I'm going to keep all of this up front, the 7.69. My final decision, though, includes me looking at the next number and seeing does it affect the 9? No, okay? If that was a 9, if that 2 was a 9, then yeah, I would increase it and round it up. But we're going to stick here, and that'd be 7.69 kilograms, final answer. Okay? So that's addition and subtraction. You're only looking at decimals. Now we get down to some that include multiplication and division. So what's important here? The significant figures, right? So this is where in your head you're going, okay, I got to count sig figs. I got to think about the Pacific and Atlantic Ocean. Is the decimal present here? No. So where do I start? The Atlantic, which is the right side. Looking at the number, I have to start counting at the first non-zero digit. So can I count that 0 as a sig fig? No. I start counting at the 2 and the 1. So there's only 2 sig figs here. Okay? Yes, I know there's an extra 0, but that's a placeholder. That placeholder is just showing the size of the number. If that 0 wasn't there, it would be 12. That 0 is there because it's literally representing this number's in the hundreds. So I need to at least write it down. It's not significant, though, in number in terms of accuracy. All right, then we have this one. We have present decimal. So we start from the Pacific. So we're going to start counting from the left in. So as I start counting, I see I'm 8 is my first digit. So once I start counting, I don't stop. So I see 1, 2, 3. 3 sig figs. Who's my weakest link? 2 sig figs. So I'm recording my final two significant figures. So when I divide these 2 numbers, you get, this is J, okay, 14.0187. What are the units? Kilometers, because you have kilometers squared over kilometers, so one of them cancels. Gives you kilometers. That's a big fat lie, though. I'm not nearly that accurate. You know, that's a 6 sig figs. That's saying I'm super accurate. Whatever I'm measuring with is very, very, very accurate. It's not. It's only accurate to 2 sig figs, so I need to adjust this. The way I round is I always start from the left side, and I need 2 sig figs, so I underline those 2, and then I look at the next one, I say, does it influence the previous number? Does the 0 influence the 4? Nay. Okay, so I record as is 14 kilometers. So, you know, the sig fig thing is like kind of foreign to you at first, but you're not changing the number. It's still about 14. It's just saying, I'm only sure it's 14. I'm not for sure it's 14.0187. It's just an adjustment of how many numbers you're recording as true. And then we have, this up here. I'm sure it's 435, pretty sure. It's not 435.2, so you're not that accurate. Okay? So final answer here. Next one, how many sig figs up here? In this one? Where do you start counting? There are 4, yes. Where do you start counting though? From the Pacific or Atlantic? Pacific, right? Because you see a decimal there, so you start counting from the Pacific. But you shall not count those first 2 zeros because they're not. You don't start until you see a non-zero digit. So you start counting at the 5, but once you start counting, you don't stop. So you're counting 5, 6, 0, 0. So there's 4 sig figs here. How many here? 3, because you start from the Pacific. Once you start counting, you don't stop, so you get to the end. So there's 3 sig figs here. Weakest link? 3 sig figs. So that's what you're recording, okay? Now, you don't have to do all this like, let me show every single thought that comes into my mind. You don't have to do this. When you get to the point where you can look at a number and go, oh yeah, 3 sig figs, final answer means 3, this is just for clarification on what I'm doing for you, okay? You don't have to show that work. But when I divide, I need to get, let's see here, I get an answer of 0.082. 028, sorry. And then I have to take millimeters cubed, divide by millimeters squared, get what? Millimeters, okay? What do you notice about my number? How many sig figs are here? 2. So because I said Pacific and I count over here, right? So how do I make it 3? Yeah, add a 0. Add that 0 to say I am for sure 0.028, and then this is going to be my estimated digit, but I still record it because it's still a significant figure, okay? So that's how you can adjust that. I think scientific notation is a wonderful thing because you can see the sig figs up front. They're in that front number, okay? So write this as in scientific notation. 2.8 what? 0, because you need all of 3, times 10 to the -2, right? Because you want to say, I need to move this baby back 1, 2, to represent what it previously was, 0.02. So times 10 to the -2 millimeters. That's why I like scientific notation so much. That's why you'll see a lot of my answers in scientific notation, because the sig figs are literally whatever is in the front right here. That's a decimal right there. Okay, so others on number 4 that you are just like, I'm not sure on. Yeah, Maggie. H. You have to tell me your number because I don't have my calculation on this sheet. So H was 4.5 times 10 to the 5th kilometers times 3.00 times 10 to the 3rd kilometers. Okay, so what did you get when you multiplied? Like the full number when you multiplied? Oh, okay. Anybody? I got you here if you don't. Alright, when you do this, I get, and this is in scientific notation, that's just with my calculator here, 3.5 times 10 to the 9 units. Everybody? Kilometers times kilometers? Thank you, kilometers squared. So that's it so far, right? But then I need to go back and double check my sig figs. How many sig figs in this number? Yeah? The 8? Did I write this down right? I got to the 9th too, Sean. Yeah.
I think you write 3.5 to the power 9 to 3. Oh, never mind that.
Okay. This is what I just put in the calculator, so if I made a mistake, I'll go back and look. When I count sig figs here, I see these 2 as my 2 sig figs, and then I see these 3, because I see decimal present, as 3 sig figs. Weakest link, 2 sig figs. So do I need to adjust this number? Yes. I see that I have 1, 2 significant figures. This third one is going to be you're using this third one to see if you need to round. Do you need to round? Yeah, so you're going to round it to 1.4, no more sig figs, times 10 to the 9 kilometers squared. Okay? So the rounding thing is just that next one that you want to record, but you can't because you need to see if it will affect that previous number you did record. Any more from, well actually I have some more I'm going to review here. Before though, I know you heard in the video yesterday all the fun we were having with just seeing how accuracy and precision work, like crumpling up with papers and stuff. So, trash your ball. Let's do this. Pull out a piece of paper, crumple it up. We're going to see who can beat my J. I got a pretty nice shot here. Let's see this. I'm going to have to do this thing. It can't be awesome. I'm going to get the 3-point line. Now, my favorite thing is okay, those two over there, go for it. Shoot. You want to get the basket? Go. Air ball, okay. Next group. Oh, okay, next group. Let's go. Yes. Oh, air ball. Two men already. Next group. Oh my gosh, these are awful. Awful. Next group. OMG, people. Whew, I'm glad. Okay. Okay, this is not going to make it, but we're going to see.
YOLO.
So, how many were accurate?
One.
There's like two. I think there were two accurate. Okay. Overall, as a group, all the measurements we took are all around here. So we can see that this big clump right here, were they accurate? No, but they are all right here clumped together. They hit that air ball so many times, right? Consistently got air ball. Is that precise? Yes, okay. Getting the same measurement a lot of times is precise. Can you be precise but not accurate? Yes, just like air ball, right? Very precise but not accurate. Can you be accurate but not precise? No, because if you're accurate, you're like swoosh, 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 right? And that means you're very true to value, but also consistently getting the shot. So can you be, I just asked you that, can you be accurate without precision? Okay, so if you are accurate, you are also precise. If you're precise, you don't have to be accurate, okay? You can consistently like airball, and not be accurate, but your precision is great. That means that you're very consistent in how you are doing your lab or measuring your values, okay? So that's all accuracy and precision is. So you solved this question, question 6, I think, on problem set 3A. Which student was more precise? Right, student 2, because what are they kind of hovering around? What value? 72.00, right? So they're all hovering around 72.00 grams. What if I told you the true value was 80.00 grams? What do you say? They're precise, but not accurate. No, if I said the true value is 80.00 grams, I don't think that's very close to 80. So I would say they're precise but not accurate. But if all of student 1's values were like 80.50, 80.55, 80.10, and 80.05, then I would say they were what and what? Yeah, precise and accurate, because all their values are very close together, they're clumped together, and also they're very close to true value. Okay, so that's pretty easy once you kind of let the light bulb come alive here. Okay, any questions on other questions on problem set 3A? Yay or nay? Nay. Okay, keep your problem sets on your desk. I'll get those shortly from you. Okay, so we're going to go through just a couple more sig fig practices with actual instruments because you guys are doing a lab today. And on this orange sheet of paper, it's got some really cool rulers. The rulers have different graduations, is what I'm going to call them, but they're just markings. So I'm going to go through the first one with you because some people were confused in my last class. They're like, I don't understand what you're asking here. So let me go through this first one, okay? This says 16, but I'm going to use, oh no, actually I do have it pulled up. Hold on. Everybody have an orange, or I have one white sheet, sorry. Orange sheet in front of them? Number 1. Okay. Okay. So looking at this ruler, really, really crappy ruler, right? Like there's no numbers here. So number 1, what distances can you be certain of? For sure, on the ruler, what distances can you be certain of? 0 and 10, that's it, okay? So 0 and 10. So you can put this in your notes or subject sheet paper. This is something I'll take up in the portfolio check as like class participation. So number 1, just put 0 centimeters and 10 centimeters. Very to the point, no complete sentences. I just want to make sure we can estimate digits from instruments, not from just not just from paper values anymore. I want to be able to use our instruments for this. So the distances we can be certain of are 0 centimeters and 10 centimeters. All right, number 2, 6 students used the ruler in Model 1 to measure the length of a metal strip. Their measurements are shown to the right. Were all the students able to agree on a single value of any digit? Look at the student values. Shout it out. What do you guys think? Are any of these 6 people, were they able to agree on any value? Look, we've got 3s, 2s, 3. All of them were not able to agree on that, even that first digit to record, right? So you can say that because, there's no graduations here. They all have to really eyeball it and guesstimate. So let's say, no, they weren't able to record something all the same way. They weren't able to agree on a single value. Okay? If yes, there's no yes. The answer is no. Number 3, Model 1 is not very useful, but a measurement can be estimated. Estimated is that keyword, okay? Discuss in your group how students may have divided up the ruler by eye in order to get the measurement that he or she recorded. So how do you think they got these values? What did they do with the ruler? They kind of split it up into like maybe thirds or quarters, and they said, oh, that's about a third of the way up, so I'm going to call it 3 centimeters. Or that's about a third of the way up, I'm going to call it 3.33 centimeters. They tried to guesstimate, so that's just dividing it by eye. And that's what you're going to have to do when you don't have graduations between 2 markings. And that's okay. But notice, estimations, there's no right answer, because everybody's going to have a slightly different version of it. Now, some of these people are, they're flat out lying. They're going, oh, it's 3.33, it's very accurate. So you can't record more than one estimated digit, because then you're saying you're sure of one and then estimating the other. You can only estimate one. Then after that point, you're lying about your accuracy. So I just wanted to do the first model with you to show that it's very simple in the answers. You don't have to elaborate much at all. So you guys go ahead with your buddy next to you. Start model 2, 4 through whatever. Try to get through 10. Okay, let's try to get through question 10. We don't have the balls. First. It is not too loud. Raise your hand for number 9. Let's finish that a little bit together. Here's some questions, so I'll try to help you here. So you see we have different varieties of rulers, so if you want to watch up here, if not, you're good and keep going through your work. Crappy ruler, medium crappy ruler, pretty good ruler, okay? So we can see the differences here. You can see the valid measurements are changing each time. So for number 9, you have to look at all of them and see from the valid measurements column, draw a square on the certain digits, the one that you know for sure, and then circle any digits that you think were estimated based on how the rulers look. So looking right here, do you guys think these were estimated or for sure? Estimated, right? Because we already went through that example. They're definitely estimated. There's no way they knew it was 3. So both of those are estimated, okay? Looking at this one, you can see that everybody agrees on 3. Well, why do you think so? Right. There's a third, 1, 2, 3. There's a marking at 3. So are they certain of 3? Yeah, they for sure know 3. So all those are certain. These other ones, since they're varying, that means that they probably are estimating that little bit that's hanging over the 3 mark, and they have to estimate where it is. So those are all estimated. And the reason I'm telling you this is because in the lab, you will have to estimate. And so if you don't record a digit there, that means that you didn't follow the sig figs rules and you're not estimating. So I'm just trying to point that out to you now. So when you go back to the lab, you go, it's not 2.5, it's 2.5 blank. If you fill in the blank, because everybody's going to be different. And then ruler C, there's lots and lots of little markings. So which ones are for certain? Here. The 3s and the 2s, right? So the 3.2 is certain on all of theirs because they could see right there, there's 1, 2, 3, and then 0.2, and then between the 0.2 and 0.3 mark, they were estimating. So these ones in the back here, the 1, the 2, and the 0, are all estimated. The ones in the front are certain. So you kind of see how it works. You get more sig figs as you get more graduations, and you get more accurate. So that's not too bad. Now, the second part, which was the circling, which is what you're estimating, we can finish that up together too. I can't, for some reason, get this to stick to this PDF, so we're just going to move this like this. Okay. So number 10, based on the examples in Model 4, circle the best phrase to complete the sentence. In a valid measurement, you record what estimated digits? Oh no, thank you. You record one estimated digit. You don't get to go frivolously and continue. In a valid measurement, the estimated digit is the blank digit or in the measurement. Last, okay? Don't estimate in the middle. That would be real funny because I would not understand what you're doing there. And then finally, in a valid measurement, the estimated digit corresponds to the blank on the instrument. Is the estimated digit the smallest marking? No, it's what? Well, Sam? Right, it's past the smallest one, because you know for sure where it is on the smallest marking. You have to estimate 1/10 of that, and the only reason it's 1/10 is because there's one decimal place back, because decimals are in tenths of each other. So 1/10 of the smallest, okay? So, I think thumbs up, we got the hang of this now. We know what we're doing. Yeah? Thank you, appreciate it. My surveys are very important, okay? So, let's go ahead and lab it up. Pull out a sheet of paper, I'm going to tell you what I expect to do in the lab. Okay. Keep your that orange paper in your desk and I'll come and get it from you. We won't have to finish the rest of it because once I see you guys have the hang stuff, I try not to, make you finish everything and just bore you to tears. So this is an inquiry lab. So you guys have done probably many labs for earth science and biology, or maybe physics or physics if you've taken other things in your life. So you guys know how to use equipment. You know what you're recording. You guys know how to graph. You guys probably know how to do the experimental method where your experimental design where you have two different variables. So I'm going to review quickly what I expect of you, and then I'm going to set you free. You have between 7 and 8 items in a basket back there. They're all different sizes. Your job is to, 1, measure the density of every single one of those. What 2 pieces of information do you need to get density? Okay, mass and volume. Mass is probably going to be measured with those. If you turn around, you can see those scales back there. So that's going to be on a digital scale. Unfortunately, digital scales don't have markings for you to estimate between. The last digit on the scale is going to go fluctuating up and down. Okay, it's haunted. It's going to just keep jumping. Just count 3, 2, 1, and then take whatever number you see because it's never going to stop moving most of the time. That is the estimated digit because it's estimating for you because it's trying to figure out is it closer to this number or this number. So you won't estimate on this. That'll be from the scale. And then the volume can be in 2 different ways. What 2 methods can you use to get volume? All right, so the length times width times height. So you can do length times width times height. What units is that most likely going to be in? Centimeters cubed, right? So centimeters cubed. And then another way to get volume is going to be what? This is on your notes, like one of the last slides in the notes.
Is it doing it in the graduated cylinder?
Right, so that method is called volume displacement. So volume displacement is where you put in a graduated cylinder a specific amount of water, so we'll put water initial, and then when you drop an item in there, an irregularly shaped item that you wouldn't be able to use a ruler with, for example, like maybe, I don't know, a sphere here, and the water rises up to a new level, that's your water final, That difference there is your volume of your item, because it displays that much water. Water is very special in this case. That's where we use water. Water has the density of 1 gram per milliliter, or 1 per centimeter cube. Because if you took a cube of water and you had a centimeter by centimeter by centimeter, and you could put that cube of water on a scale, how much would it weigh? 1 gram. Okay. So these are interchangeable for water. So that's why it's okay for us to record density as 2 different units. It can be grams per centimeter cube or grams per milliliter. So that's why I say 1 milliliter is equal to 1 centimeter cube, because it does not matter how you record it, or record it based on how you measure it. Okay. After you find the density of everything, now you of course are going to be recording all your masses, all your volumes, and all your densities, because that's a good lab. Okay. Record everything for me to correct sig figs, and you're going to line up your items in increasing order. Snapshot, send that to my email. If you download the Selly app, you can text that to me. After that, you're going to then be graphing your density, your volume versus density. This would be X and Y. It's going to look like a scatter plot. It's going to be okay. You're not going to connect the dots or anything. It's going to look like a scatter plot. After that, if you get to the rest of the questions on the lab sheet, which I'll show you when you get back to your lab, that means you're a very effective group. You have divided and conquered. You have said, you mass, you volume, we're going to do the density, and then collaborate. That means you're an effective lab group, and I always give you extra credit for that. So that means if you get to the questions after this, extra credit, okay? So I like to reward hard work, because it's kind of required in this class, okay? So I think we're good to go back to the lab. Let's go back here and I'll show you the lab technique. Same lab group as yesterday. Who has been in a group? Maybe remember Sarah's group, thank you. Oh, Sarah. Pull out the notebook that I showed you underneath the cabinet. The additional questions in a little bit is in your notebook. It's probably about 4 or 5 pages back. It says density of a solid inquiry, and it's got a little bit of information on it. You can use that as guidance, and I also leave that off on the board. So everything's in your little bucket at your desk. You have analytical real scales there. If you need a bigger graduated cylinder, I have a 500 here. It's flat, so break it. If you need more graduated cylinders, I have the cabinet open. Everything else though should be underneath your cabinet or your drawers. Okay? I'll be around for questions.